By the mid-1800s, steam power and iron-hulled ships had accelerated global trade to a velocity that humans had never experienced. Massive quantities of raw materials were suddenly crossing oceans in weeks rather than months. But there was a structural bottleneck. While physical transport had moved into the industrial age, the systems used to track those goods were still dependent on handwritten ledgers and the physical delivery of paper. This created a kinetic administrative asymmetry, where the physical volume of mechanized trade far outpaced the ability of paper-based counting houses to process the data. The stakes were immediate and physical. A shipping industry that unloads coal faster than it can process the bills of lading quickly becomes a graveyard of lost shipments and portside gridlock. Without the benefit of microprocessors or digital memory, Victorian engineers were forced to invent a sophisticated, entirely analog software stack to keep this global machine from seizing up. The first bottleneck was ocean latency. In the 19th century, shipping updates took half a year to travel between London and India. The solution was the all-red line, submarine telegraph cables that dropped transoceanic communication times to mere seconds. Because the network was designed with deep physical redundancies, a single severed cable wouldn't stop the flow. Messages could be dynamically rerouted through dozens of other British-controlled nodes to reach their destination. But this instant transoceanic speed created a local logjam. Thousands of messages flooded into central telegraph offices, where they still had to be transcribed by hand and delivered by messenger boys through crowded city streets. To solve this urban gridlock, Josiah Latimer Clark pioneered a subterranean network of pneumatic tubes, the analog equivalent of a local packet switching network. By utilizing compressed air and partial vacuums, telegraph hubs could blast physical data packets directly to stock exchanges and post offices, bypassing street-level congestion entirely. By merging undersea cables with pneumatic distribution, the Victorians engineered a high-speed hardware bridge that successfully connected localized urban markets to a global network. Even with the hardware in place, there was a bandwidth crunch. Telegraph companies billed by the individual word, making the transmission of complex logistical instructions prohibitively expensive. Commercial codebooks provided the solution. They functioned as manual data compression algorithms, mapping complex sentences about cargo weights and port arrivals onto single 5-letter code words. Because these codebooks were standardized internationally, they acted as a universal API. A merchant in Hong Kong could send a code word that a London banker would decode in seconds without any translation errors. As trains and telegraphs tightened the network, they exposed a lethal confusion at the heart of the system: the lack of standardized time. Historically, towns used local solar time. This meant that when it was noon in London, it was 11:43 in Plymouth. For a single-track railway, these 17 minutes of difference were the difference between a safe passage and a head-on collision. To sync the network, the industry adopted standard railway time. Master clocks at Greenwich transmitted electrical time signals over the telegraph lines, instantaneously synchronizing every station clock in the country to a single master. Standardizing time and data protocols effectively decoupled global commerce from the friction of local solar cycles and human language barriers. On the physical oceans, high-volume trade created a severe moral hazard. Unscrupulous owners were intentionally overloading ships and heavily insuring them, leading to the regular loss of coffin ships and their crews. Samuel Plimsoll, a social reformer, campaigned for a safety standard that was impossible for ship owners to hide or manipulate. The physics of the problem were complex. A vessel's buoyancy changes based on the density, temperature, and salinity of the specific water it's floating in. A ship that looks safe in the cold North Atlantic might sink dangerously low in the warm, fresh water of a tropical port. Plimsoll translated these hydrostatic variables into a hard-coded physical algorithm. By painting the load limit directly onto the hull, the invisible calculations of displacement became a visible, instantly auditable data point. This symbol secured the physical endpoints of the trade network, ensuring that the drive for volume never exceeded the physical limits of the hardware itself. By the turn of the 20th century, the Victorians had integrated global communication, synchronized time, and risk management into a responsive network, all without ever utilizing a single transistor. Modern digital innovations like JSON payloads, packet switching, and global API systems are the direct conceptual inheritors of these analog protocols. The Industrial Revolution did more than just mechanize labor. It authored the underlying logical architecture that we still use to navigate the information age today.